Before we get started, I'm going to walk through a couple of quick rules just to make sure that we're all on the same page. So, when we're doing some science, what do we think is a good rule for while we're doing science? Yes, ma'am?
No running around, no yelling.
No running around is a good part of it. I think I heard the start of it for you.
When you need to go to the bathroom, don't go without permission.
Okay, that's a good rule as well. We'll get to that piece in a second. Yes, ma'am?
Always do what you say because you can't do something wrong.
That's important. So I'm gonna consolidate some of those rules, and I'll say that our first rule is to be safe.
That's what I was going to say.
Oh, I'm so sorry I missed you. I didn't see you out the corner of my eye. My apologies. But yes, you are absolutely right. Our first rule is to be safe because we're going to be working with things like electricity and acid and fire. And I want to make sure that everyone stays very safe, so everyone stays back away from the table. If I give you something out at your table, do you think that you should eat or drink it?
No.
No, you shouldn't do that. That's wise. So things like that, just being safe while we're doing science. Our second rule, some of the folks over here got to it, but what do we think is a good rule for when we're trying to learn something? Yes, ma'am? Following what I say, very nice. Listening, very important. Yes, ma'am?
In my school, we do it, we think ourselves as scientists, so our teacher always says to write a hypothesis first.
We will get to that in just a minute. But yes, what do you think?
We have ask if we have a question.
Very nice. So those all work together to be respectful. So I'm going to ask everyone to be respectful. First of all, being respectful to me, because there's a lot of you and there's only one of me. So when I'm talking, I'm going to ask that everybody listens. If you think that you know the answer to a question, you can raise your hand to let me call on you. I think everybody already had that one down. And being respectful of each other, so just making sure that everybody is taking care of each other and being in a good place, so that we can follow our third rule, which is a good rule for a party. Does anybody have an idea for a good rule for a party? Yes, ma'am.
Have fun.
Have fun! Yes! That is our third rule. Our third rule is to have fun, because we're going to be doing a lot of cool stuff with electricity and acid and fire, and it's going to be a lot of fun. So we're going to be safe, we're going to be respectful, and we're going to have fun, and that is going to be our excellent time together. So before we get completely started, I did want to ask whose birthday it is.
Akshita.
All right, and what is your name?
Akshita.
Akshita, very nice to meet you, Akshita. I'm going to have to ask your help to start me off. So I'm going to start with an experiment. What does this look like to anyone? It looks like a fake dollar. Yes, I heard the fake dollar. So if I were to try and put this in a vending machine,
Will it work?
not really. Don't think so. Don't think it would work. So I feel like if I'm going to be doing this highly technical science, I should be getting some reward out of it, right? So I'm going to see if I can transform this fake dollar into a real dollar.
I see that.
That is what I'm going to do.
I don't know. I saw this trick before.
So I want you to hold on to this for me. And we're going to see what happens when we light this on.
Why? Oh, I've seen this trick
It's
before.
transform. Oh no. Oh no. No. This isn't what I wanted to happen. This is not what I wanted to happen. We have to put out the fire. I hope that it's. That was unexpected.
I know what you
So what do we think? What do we think it is now? Did it turn into anything?
A real dollar bill or I don't know.
Does anybody remember our rule? What do we think it is?
Either a real dollar bill or coal.
Okay, so we've got two choices here. It either did what I said it was going to do and will turn into a real dollar bill, or it just burned up. Because burning up is one of the kinds of chemical reactions that we have. If something burns and it changes into ash, that's chemical reaction. So let's see, does anybody have any other guesses as to what it might be? No, we've got our hypothesis. So if I can ask
Open it.
Akshita to open for me.
Is it real?
It turned into a real dollar! What? That shouldn't have happened!
I knew it!
That shouldn't have happened!
I just burned here. Yeah, me too.
I see that we've got some smart folks in the audience here.
I know. Oh, I know what's
This is what's called, by magicians, a dove pan. So you put something in the bottom pan, and you slam the top pan down on it. The top pan is hiding another pan up inside it. So that was where I had the real dollar to start with. And then when I pull it down, normally, when it works correctly, it gives you the empty part. So I wanted to show this. Was that science? No, that wasn't science. That was magic. That was a magic trick. So if I were a magician, would I have shown you the trick?
No.
A magician would want you to keep trying to figure out the trick. They would want you to be mystified. A scientist will try and help you understand what's happening. That's the difference. Magicians will want you to be confused. A scientist wants you to understand and will explain whatever it is that we do. But part of what we do is being safe. So I'm going to put on, since I'm starting to do actual science now, I'm going to put on my actual science protective equipment of gloves and goggles. This is just to help.
That's just like a real scientist?
Yes, that is exactly what real scientists will do. They'll wear nitrite gloves and safety goggles just like these. They'll be doing slightly different kinds of science most of the time, but they'll also be using some very high-tech science equipment that I know none of you have actually encountered before. This is rare. This is exciting. This is a plastic bag. With water in it. Yes, you're absolutely right. This is a plastic bag full of water. It's not that rare. Have people seen this before? Yeah, you've seen it before. Well, I bet that I can do some cool science with it anyway using another piece of rare scientific equipment.
I know what you're going to do. I know what you're going to do.
Do you? Well, all right. I'll entertain some hypotheses. Going back to our original question here. We've got our baggie of water. We've got a sharp object. So what do we think our hypothesis would be if I were to jab the pencil into the bag of water? Start with you.
Water wouldn't fall out.
That water won't fall out. All right, an interesting hypothesis. We have any other takes? Everybody thinks that the water's not going to fall out?
Yeah. Yeah, I think that.
Does anybody want to risk it?
I don't know.
Who wants to stand under the bag of water?
Me! Birthday girl!
All right, I think our birthday girl has earned the spot. Akshita, here we go.
Nothing will happen. Trust me, nothing will happen.
Here's our moment of truth.
Nothing will happen, Akshita.
3, 2, 1.
Nothing happened, Akshita. I knew it. I knew that.
Nothing comes out. So what do we think caused this to happen? Can anybody explain? Yes, ma'am. What do you think the explanation is?
I think because you put the pencil in slowly, so it made a hole, and then the pencil went in through.
So you think it has to do with the fact that I put the pencil in slowly? Yes, ma'am.
I think that because if you take the pencil out, water will escape, because the pencil is trying to block the hole from water coming out.
Okay, so the pencil's blocking the hole from the water coming out. Anybody else have thoughts about it?
Same thing.
Same thing. So you're absolutely right. The pencil is blocking the hole, but I think that we raised an interesting question that's worth testing. If I try and jab it in faster, will the same thing happen? Do you want to try again?
Yeah.
You want to test your luck? Come on up. We're going to test our luck. All right. Here we go. This time it's just going straight through. 3, 2, 1.
All
right. So it doesn't necessarily have to do with how fast it puts in. Yes, ma'am.
I think it's a special kind of plastic bag. No.
It's not. This is just a normal plastic bag. Yes, ma'am.
Maybe because it's filled to the brim.
That is a part of it. You're absolutely right. So I'm going to go one step down from you. Things like plastic bags are called polymers. Plastics, rubbers, and things like that are called polymers. And what a polymer is its molecules. All of the little pieces that make up that polymer are made of long, stringy, stretchy molecules. And those chains of molecules all are able to wrap and tangle up around the pencil. So it's like getting chewing gum in your hair. Has anybody ever gotten chewing gum in your hair?
No.
No.
And I don't want to.
Normally, you are actually the first group I have ever done that has not had someone get chewing gum in your hair. Good job.
What?
So, but yes, if you get chewing gum in your hair and it gets all tangled and clumps up around there, it's really hard to get out, right? So that's what's happening here. The molecules are tying up and tangling up around the pencil, and none of the water can get out. So, do we think that the same thing would happen if we tried
Okay, I've seen this trick before.
a paper cup? If we tried to jab it over a paper cup, do we
It
get the
won't
same
work.
thing? We don't think it'll work? Well, there's only one way to find out.
I don't know. I don't know yet. I don't know. Yeah, look what's happening.
that didn't work. So, even if you manage to get the pencil through, it just tears the paper, and you end up with a hole. And so the paper and the water will come out. So the paper cup is not a polymer. It doesn't tangle up and clump up in the same way that plastic does. But, you know, something that is a polymer
It's balloon.
is the rubber elastic in a balloon.
Oh, I know what's going to happen.
So we're going to test something else. One kind of chemical reaction we already saw is turning something into something else. So let's see what happens. Does anyone have a hypothesis about what happens to the balloon?
Probably it would like pop.
You think it'll pop? All right, do we have any other hypotheses? We've got some people preparing on this side. Only one way.
I'm sinking. I'm sinking.
I'd say your hypothesis was correct. So everybody kind of saw that one coming. So I think if we do it again, we should get the same.
It won't happen in my chair. I'm pretty sure it won't happen. I don't know. Yeah, I don't know.
Huh.
I know.
So that one didn't pop when I put the fire on it. Who has an idea? Yes. Akshita.
Because you didn't touch, the fire didn't touch the balloon.
You think that'll have something to do with it? Yes, ma'am.
I think the balloon has a special,
You think the balloon is covered with something special? Any other ideas?
that it's like filled with less air.
That there's less air in it? Okay, interesting. Yes, ma'am.
That you put the fire really like, for the other one you put the fire like hardly, and then for the one you didn't really use the fire that hardly.
So I'm going to see if we can do it and get the same result. I'm going to try and
I'm gonna sink down.
get it right up next to it,
Sinking.
and it's not popping.
What? What? I'm sinking.
Do you want to know why?
There's water in there.
Yay! What goes that?
There's water. Whoa, what? I knew
There was water inside. So the water. So what about the water would stop the balloon from popping? Yes,
Because
ma'am.
water is cooler than like candle or fire.
So because the water was cooler, that might have helped. Yes, ma'am.
And like what she said, but like the balloon was protecting it, so like the fire wouldn't like. Well, yeah.
You're on the right track. Yes, ma'am.
So the water is kind of like filling up the air, and the air would have like made it pop because it's like, and like the water is kind of causing it not to pop.
So the water is causing it not to pop, and it's for something like the reason that you were saying, but backwards. The water absorbed the heat from the fire much more than the elastic from the balloon did. So when I only had the balloon, the heat caused those polymer molecules to get all riled up and try and get away from each other. And as it spreads out, that causes the hole that causes the balloon to pop. But when I have the balloon full of water, or with some water in it, the water ended up absorbing that heat instead of the balloon. So that way the balloon's molecules stayed nice and tight together. They didn't pop, and it was only the water that was heating up. So different things react to heat differently. That's an important part of the chemistry that we're doing today. And to give you an example of that, I'm going to show you another experiment. So remember our dollar that we had earlier.
Yes. Oh, I know what you're gonna do.
So our dollar that we had earlier, I've had it soaking for a little bit. So we've already learned that things react to heat and fire differently. So how do we think that the dollar is going to react to the fire now that it's been soaking? Yes, ma'am.
Like the balloon, I think it's not going to really make an ash.
Okay. What do you think?
I think it like will become into ash.
Okay, you think it'll burn into ash? Yes, ma'am.
If it was normal water, it'd probably burn to ash. But there was a certain chemical that was in the water that you have that made it, that would probably not make it burn.
So we don't think it'll burn then. Do you think it'll light at all? Well, so here's what we're gonna do. We're gonna test it.
There's a chemical.
And we're gonna see if the dollar lights on fire or not. Okay, let me adjust it a little bit here.
It's not burning, I'm sure. I knew that would happen.
But wait,
It's not ash.
it didn't turn into ash.
I knew that.
It lit on fire, but it didn't turn into ash. Who thinks they have an idea? Yes.
I think you put something else than water.
You think it's not water? How about you?
I think the water is covering the dollar from getting burned.
So you think the water was preventing it from getting burned, but would it have lit on fire like that if it was all wet? That's the key thing. Yes, ma'am.
It's there's a chemical in the water that's making it burn like that.
Okay, so you think it's a chemical as well? Yes,
I
ma'am.
think like that because the dollar's made out of paper, it's still burnt, but then the water absorbed the heat and then it like stopped.
Okay, so we've got a couple of competing theories. As it turns out, you're absolutely right. This is not water. What we have here is something called isopropyl alcohol. Some of you may have it around your house as rubbing alcohol. And rubbing alcohol has a very low burning point. It lights on fire at a very low temperature. Whereas the dollar, because it's made of a special kind of paper, has a very high burning point. It doesn't light on fire at the same temperature. So when we light the dollar on fire and burn the alcohol burns very quickly, but the dollar does not burn at all because it never reaches the high enough temperature to burn it. So that's why our dollar, and also it becomes completely dry when it does that. That's really fun.
What?
Yep. So yes, we've learned about things reacting differently to fire, to heat. We've learned about how polymers interact with one another. So there's other things that we have to be careful of when we're working with science besides just fire, though. Would we want to be careful around acids?
Yeah.
Yes, we would want to be careful around acids. And for that reason, I should warn you, I'm actually part dragon.
No.
What?
My great-grandfather, he was the true dragon in the family. He told me all about it, and as it turns out, we dragons don't actually breathe fire. We breathe acid. And yes, we breathe acid, and I can prove it to you. I can prove it to you because I can use my acid breath to burn the pink right out of this juice. Yes, ma'am.
I think because it's going to turn like clear.
That's
when you blow it.
that's because of my acid breath. That's exactly what's going to happen. Yes, ma'am.
I think you don't have acid breath, and I think the thing you're gonna blow into is acid.
So you think that it's acid and that my breath is not acid?
Yeah.
Yes, ma'am.
Vinegar is the most weak acid.
That is a very weak acid. You are absolutely right. So my breath is also a very weak acid, so that's why it's safe to be in the room with me. But I'm going to use my acid breath to burn this out of the juice.
Nothing's happening.
Nothing's happened.
Nothing.
Nothing. But it's becoming clear a little.
It's making more lighter.
Oh my gosh! What is happening? Still